Thank you so much, Frank, and the crew, Barry, Neha, and Rodrigo. Thanks so much for everyone for joining. I know that we were supposed to have Ken Cousin today. I'm sure you're going to enjoy his talk and his amazing delivery of yet another talk as soon as the next opportunity arises. But I'm thankful to be here today, and I want to talk about the topic of functional programming. But I want to talk about it in terms of three different languages. So we'll talk about functional programming in Groovy, Java, and Kotlin, compare and contrast a few things that I want to touch upon along the way. The best time to ask questions or make comments is anytime you have a question or a comment. Don't hesitate. Please do raise your question or a comment along the way. Neha has graciously agreed to present them to me along the way, and I'll be delighted to answer your questions anytime as we go through. So let's get started. So we want to talk about functional programming. We want to talk about it with respect to these three languages, but let's just step back a little bit and talk about the programming styles to begin with. Well, every one of us, I'm sure, have used and are very familiar with the imperative style of programming idea. So we've all used imperative style. Well, let's talk about Java and the JVM itself. I'll say Java of the past, if you will. So what we did in the past was an imperative style plus the use of object-oriented style of programming. So you may wonder, hey, we do object-oriented programming in Java, right? Why talk about imperative style of programming? Well, I want to say that imperative style specifically in terms of what it means to program is where we tell what to do and also, that's the key, how to do it. So that is basically what we do in imperative style of programming. Now, obviously the question is, we do OO programming, where does imperative programming fit in? I want you to take a really crude analogy. Let's say I want to build a wall to a particular room. So I'm putting up the bricks for the wall and I lay the bricks on top of each other and step away. Quite dangerous, isn't it? Because by the time I step away, the brick may actually fall on me. That's not the way to build any wall. So what do you normally do? You take the bricks, which are your objects, but something has to connect those objects together. So when you're programming an object-oriented programming, you want to iterate through a collection of objects. Or you want to take one object and call a method on it, take the result and call a method on another object. That's what I mean by you got something to connect those bricks. Well, you could put clay together and connect them. Nothing wrong with that. We have done that in history and building, or you could use cement to build it. So that's exactly the point, is you can take these objects in Java, but you can use imperative style to work with these objects, or you can use functional style to work with these objects, clay versus cement, if you will, and I'll let you choose which one is which. But the point is, we're not doing something instead of object-oriented programming. We are doing something in addition to object-oriented programming. How do we glue these objects together? How do we work with these objects together? And we don't need to use objects if we don't want to, but we don't have to shy away from using them where it may make sense. So in that regard, let's talk about the imperative style of programming. So let's say we want to start with some names is equal to, I'm going to say list of, and let's create some names I want to work with here. So we created some names for ourselves, but I want to be able to iterate through these names. How would I do this? Well, you can say for I int equal to 0, I less than, and tire ourselves with all those details. But alternatively, what we could do is we can say for, and we could say, for example, name, where the name comes from names, for example, and then we can simply say, in this case, output the name and display the values in here. So it displays all the values. That's, of course, Java code, and we were able to iterate through these collections in the imperative style and display the value. Well, if we were to take these exact names that you see here, and I'm going to say, here comes the names is equal to, let's go ahead and say some names like we just did it a few minutes ago, but I want to be able to iterate through these names and print them. So we can say name in names, and I'm going to simply go ahead and print those names right here. So if you go ahead and print that out, I can say name and display the result of that particular computation. That's Groovy code right there. A little bit more, less noise fancy, if you will, a bit more elegant and fluent, but it's doing the same thing that Java did in the imperative style. Or alternatively, we can go back here and say names is equal to list of again, and again comes the some names over here. And then we can simply say a for name in names again, much like what you saw in the Groovy side. I'm going to say name and printed, and that's basically the Kotlin code doing the same iteration as you saw before. So essentially, we were able to write the code in Java or in Groovy or in Kotlin, but pretty much doing all the same, the imperative style of programming. But on the other hand, declarative style of programming is something we also have used in the past. So what is really, pardon me, a declarative style of programming? Declarative style is where we tell what to do, but not how to do it. So essentially, you don't focus on how to do it. You only focus on what to do in your application code. So, but the question is, where is the how? Well, the how is delegated to other functions. That's right. Delegation, you give the responsibility to other functions. So for example, if I want to know if our good friend Nemo is in this collection, you don't have to iterate through this and say if name dot equals Nemo. You don't have to work through all those difficult code. Instead, you can simply say in one shot, you can simply say names.contains, and you can say Nemo and be done with it. Well, that's declarative style of programming. And quickly it said, yep, Nemo is there, and gave you a response. And pretty much the same code you can write in Groovy and Kotlin with a few slight difference in syntax, but nevertheless, it's still declarative style of programming. So we talked about the imperative style and the declarative style, but what in the world is a functional style of programming? Well, functional style is really exciting, but why so? Because the imperative style that we talked about has, I'm going to say, more accidental complexity. So what is really accidental complexity? Accidental complexity is a complexity that comes from the solution we choose for a problem, as opposed to an inherent complexity, which is a complexity comes from the problem space itself. Well, on the other hand, a functional style of programming has less accidental complexity. But why? The reason is functional programming style is declarative style of programming. So I'm going to say this is actually an equals right here, and a functional style is actually a declarative style plus the use of higher order functions. So this is what makes it really interesting, is the functional style is declarative style plus the use of higher order functions. And so not all declarative code is functional, but all functional code is declarative. So the nature of reduced complexity in functional programming partly comes from the less accidental complexity that's part of declarative style of programming. And that's one of the reasons why I like the functional style, is that it's declarative in nature and we can benefit from that. But what in the world is functional programming, however? Well, it turns out functional programming is based on Lambda calculus, but essentially we work with what are called higher order functions. So what in the world are higher order functions? Well, that's one of the first things we want to really think about. So rather than in the past, and I can simply say Java of the now, you can do imperative plus functional plus object-oriented programming, but that's because Java now has Lambda expressions and the ability to create higher order functions. So let's take an example of what that really means. So if I say thread is equal to new thread, and I'm going to say thread.start, and I'm going to then say in main right there. And when I run the code, it says in main. But I want to say here new runnable, and then within the runnable, I'm going to say public void run. And within the run method, I'm going to say output, let's go ahead and say in this particular case, in another thread, let's say. Well, if you look at this particular code right here, it's going to execute the main, but it shows the another thread as well. But this was a very ancient code we wrote in Java, but that's because Java once had an ideology that everything must be objects. But now they realize, wait a second, we don't have to pass an object after all, because if our purpose is to pass a function where that function takes no arguments and the body of the function is simply that code right there, then we don't have to waste so much effort in calling that particular function. So I just reduced code rather than adding code, and the program still does the same thing. But the thread in this context is a higher order function. But why? Because we are able to take a function, an anonymous function nevertheless, and we are able to pass that function to the thread constructor. So in this context, you can say, for example, a thread constructor is a higher order function. So why is a higher order function? Because it can receive a Lambda expression, right, or an anonymous function, as a parameter. So in other words, a higher order function may receive a function as a parameter, or it may return a function as a result. So in other words, much like how we can move objects around, we can move functions around. Here's another silly example. Imagine we are sitting around dinner table, and we are having a nice conversation about the sports and the movies and the politics and everything else in the world. And I lean over to you and say, could I ask you a favor? Could you please pass to me the pepper shaker for me? I want to spice up my food a little bit more. Well, you may reach over and pass me the pepper shaker. Well, that's an object you handed over to me. But a few minutes goes by and we're talking about food, and I then lean over to you and say, do you mind writing that recipe for me of the one you are talking about? I'm very curious. I want to go try making it. Now what you're giving me is not an object per se, but a bunch of instructions, a code, a recipe. And the recipe tells me how I can go home and make that food you've been talking about so nicely. So essentially the idea here is, rather than passing an object, you're passing instruction or code or a function over to me. And that's basically the idea, is not only can we pass objects around, we can pass these functions around as well. So that opens up the door for programming with these functions. And one of the essential things about functional programming, or the functional style of programming, is this idea of function composition. So what is functional composition? Well, here's a simple way to think about it. If I ask you, what is this? You're going to say, gosh, that looks like a pen. You're absolutely correct. It's a pen. But as humans, we are really good at abstracting things out. So when you identify something, you say that's a pen. But sometimes we go a little beyond it. And you realize that while that's true, it's a pen, I can realize that I've got a little lid made out of metal here. I'm going to put that down. There is this little, spring right there, not the weather, not the framework, but the metal that's a spring, that's right there as well. Then there is this little casing, which itself has a metal tip and of course has a plastic, and there's ink inside of that. Then of course I can start dismantling these parts. Now I'm going to ask you, what is this? And you say, well, that was a pen, but you broke it into multiple pieces. Well, that is true, but we know what this is called. This is called object decomposition. In other words, we are able to make objects by way of using other objects. And suddenly you realize, oh my goodness, this object contains literally maybe billions of atoms and microns and protons and electrons. And then we say, well, that's a pen. Well, the point really is we can build bigger things and more capable things using smaller things. In a similar way, imagine that I have one function with me right here, but I also have another function with me. And you ask me, what's this? That's a function. What's that? That's a function. But I can have a function which wants to accept another function as an argument, and I gave this function, or I put that down and I pass a different function to it. But on the other hand, I quickly realized why not take the first function and take the input, process the function, and take its output and connect it to the input of the second function and process and get the output. And all of a sudden, I had two functions with me, and now I have one function with me. And now I see not the parts, but the entire function that I created, just like the pen we talked about. But in this case, it becomes what's called the functional composition. In other words, a function is composed of these smaller functions put together, and we can achieve that kind of functional composition where the data flows from one function to the next function to the next function. In other words, we are able to achieve this functional pipeline. So functional composition can lead us towards a functional pipeline, and that's a very powerful operation. Let's entertain this thought just a little bit to see this nature of pipeline. We have this around us all the time. I can say source, some data.txt, and I can pass that to maybe a particular pipe in Unix system, and I can do a grep of some word, and I can then pass it to maybe an awk command or a set command of some sort, and then I can pass it to a wc-l, and then you're like, what just happened over here? Well, that's a source of the data, but guess what? The grep is a filter operation we performed, and the map is the awk is the map operation we performed, and wc is the reduce operation we performed. But that's not the end of it. Here I am actually in my basement, and it's pretty cold day outside, and of course I could be shivering here, but fortunately no. But how so? Well, there's the air, but I send the air through a purifier, and then I send it to a heater, and then of course that goes through the room, and you can see that nature of the pipeline that we are dealing with. Or I could take water, for example, send it through a purifier, and hopefully a different purifier, and I could send it through a cooler, if you will, and of course we can take a cool water and we can drink it, and you can see this nature of pipeline, a composition that we see along the way. So going back to this example we talked about, we can say, for example, names is equal to, let's start with that, is equal to a list of, and I'm going to say some names I want to start with here, but I could then say, for example, names.stream, where, well, actually let's not do the stream for a minute. I could say for each, and I could do, in this case, given a name, I could say name, and I could print out that particular name right here, and you can see the list of names being printed along the way. This is Java, of course, so we can print the names along the way, and we can see the output coming through, and you can see the printout of the names right there. Or I can say, hey, given the names, give me an internal iterator, and I'm going to filter, given a name.length is going to be equal to 5, and only give me the names whose length is 5, and we print Bruce and Darla, and that's the pipeline we are talking about. So you take the source of the data, you pipe it through the filter, and then through the for each, and you're printing that out. Think of this like you open the faucet and you have water coming through the pipeline, and the water got heated in your heater, got purified, and you get a nice warm water which is purified. That's kind of the idea, is you have this pipeline. So when you think about functional programming, think about this pipeline of operation. That was in Java, but I can go back here to Groovy and say names, for example, dot, and I could say for FindAll, where I can say, given a name, I want a name.length is equal to 5, and then I can say over here and take each one of them, and given the name, I just simply want to print the name that's given to me. So I can write the Groovy code in a similar way. Of course, you may say, hey, you can shorten this even further. Sure, we can look at that a little later on. And similarly, in the case of Kotlin, rather than the imperative style, I can say names dot, and I can do a filter. And in this case, I can say, given a name, go ahead and say name dot length is equal to 5, and then of course take that value and say for each, and I want to simply say, given a name, I want to print that name out here in the case of Kotlin and display it so you can go through each stage of this operation and you can print it. So we wrote the code in these three languages, some subtle syntax differences, if you will. So in the case of Java, as you can see, we performed this filter operation from the iteration, and we asked it to print the names which are of length 5. In the case of Kotlin, you can do a little bit of simplification here. You can say if there's only one parameter coming in, you can use an it to convey that parameter, and similarly like so, you can simply say it.length is equal to 5, and you can use that a little simplification if you had exactly one parameter coming into that anonymous function or to that lambda, if you will. On the same note, in the case of Kotlin, you can also do a it, for example, say use the same notation to say that one parameter I want to use, or you can also go to Kotlin and say, hey, I want to use a method reference on the print line right there, and I could have passed a it to it if I really wanted to, but I can also use a print line and I can call that method as well. But of course, in this case, because I'm passing the method reference, I'm going to simply use a parenthesis to pass it, and you can see it takes the print line function and fires it off. And as you would point out to me, you can do something similar in the case of Java as well, and you can use a method reference like so, and you can see the languages offer very similar capabilities, even though that may be a bit of a syntactical difference in them, as you can see. So that shows us how we can use a filter operation. But when you look at this pipeline, in the case of programming with structured programming, you are imperative style of programming, you do, for example, a for loop, an if statement, a while loop, a do. Well, in functional programming, you got a few tools of the trade. One is a filter. So the filter function, how does that work? If you have a collection of n values coming in, the output will have 0 less than or equal to number of elements in the output less than or equal to n. So you could have all the elements, none of it, or anything in between. But one thing can be guaranteed with the filter is the output is a subset of the input. So you cannot have a new element somehow pop up and say, hello, that's not going to happen. It's going to be a filtering. So it throws away some values and delivers a few other values. So here in the case of Java, we were able to use a stream and do filtering. In the case of Groovy, we took the collection and did FindAll, and you might be curious about it. If you take this particular collection given to us names and print it, you notice that it is a collection of names, but out of curiosity you say, but what in the world is this, right, that we are dealing with right now? What is it? Notice it's actually Java util array list, and you say, oh my goodness, how in the world does Java util array list have that method? Well, that's because Groovy has taken the JDK classes and nicely enhanced it with some of these nice functions so we can enjoy them on the collections we use in Java, but with the greater fluency and flexibility that you have in here. So FindAll is a method that comes way of Groovy method extensions into it. And then of course the each method as well, we are able to call on it in this case. And these were available in Groovy even before the time of Java 8, when it started introducing the functional style into Java. Groovy has had it for a long time, even before that. Well, what about the map operation? Map is really a transformation operation. So given n values and a function f of x, the result is a value of y, a collection, let's say, of y. So collection of y, where yi is equal to f of xi. So essentially, you apply the function on each element in the collection to get the result on the other side. So let's take a look at an example of how that actually works in here. So I do a map operation. I take the name and say, to uppercase, and I perform a transformation like so. Now you can see the Bruce and Darla appearing in uppercase right here. That's because we performed a map operation. So I took each value that's coming through and transformed that value. It's kind of like your heater taking the water coming in, heats up by a few degrees and sends it out. That's basically what the transformation is doing. In this case, the transformation of data. Now on the same token here, in the case of Groovy, I use a function called collect. Don't confuse this collect with the collect in Java. This collect is collecting the results into another collection, but while transforming it. So I can say in this case to uppercase and perform the transformation like so, and Bruce and Darla again appear in uppercase. In the case of Kotlin, on the other hand, I can do a map operation and I can say it dot uppercase, and I can ask it to perform the transformation to uppercase like so, and that's performing the transformation, and the output shows Bruce and Darla in uppercase as well. So we did the filter and we did the map operation also in here. Well, that brings us to the last function in that functional pipeline series that I want to talk about, which is the operation of reduce. And what in the world is a reduce? I want you to think about for a minute the gym that you go to, and on the gym, you want to work out. Maybe you want to do some planks, or you may want to do other kinds of core exercise. So on the gym floor, you put a little mat on the floor, right? And then you work out on the mat. But when you're done working out, what do? Well, you fold it, obviously. So you can take that mat and you can fold it. Let me try to fold it right there. And once you fold the mat, you create like a cylinder out of it and you stack it up against the wall and then you walk away. So essentially, you take the mat and you fold it. Well, that's kind of what a reduce operation really is. So you're given a collection and you are folding that collection into something little different. It could be a collection or it could be a single value that you want to roll it into. So in this example, if I were to go back and say length over here, because I just want to get the length of these names of length 5, if you will, kind of a silly example here. We know that each one of them is going to be 5. And similarly, I'm going to go back here and say this is going to be a length as well in here that I'm going to bring in. And then finally, in the case of Kotlin, I'm going to take this and give you the length as well, as you can see in here. So going back to Java, you can see it printed the 5 and 5, and so did the case of Groovy, a value of 5 and 5, and so did Kotlin with the value of 5 and 5. But I want to total those values together from the output. So the question is, how would I be able to total those values into one? I'm going to show you a couple of different options to do it. The first one here is to go in and say, first of all, let's say a var result is equal to, and I want to print the result when we are done here in the very end of this. So let's go ahead and output the result. But in here, I'm going to say a dot reduce, and this is going to say start with the 0. A total is the accumulated value, and then I'm going to say the length that's coming in, and I want you to return from this a total plus length as the response from this particular call. So essentially the result is a 10, and similarly in the case of Groovy, I can say here we go, but Groovy calls it the inject function, and then I'm going to say a total, let's say comma length. And then I'm going to say in this case a total plus the length. And what do I want to do with it? Well, I'm going to take that result and store it as a result is equal to. And then in the very end of this, I'm going to print the result out here in the case of Groovy. So we're applying the inject function. Likewise, in the case of Kotlin, I'm going to go over here and say result is equal to, and I will come back here and print the result like so and say here comes the result. But then what I'm going to do here is to simply say, hey, I want to do a fold where I take a 0, and I'm going to say here comes a total and a length. And what do I want to do with these total and the length? I'm going to say total plus the length, and I want to add them together, and I'm going to return the result back to the variable called result, and then I'm going to print it out in the very end of this. So that's basically what we are doing here, is to ask it to bring those values. Let me try a little bit here and provide that particular lambda expression like so, and ask it to write that particular operation of totaling the values. Well, given this, of course, I'm going to mess with that in a minute. So, but there are a couple of things we can actually do to ease the pain in the case of these languages. Not a whole lot in the case of Java, because you said reduce 0 and the lambda sits right there at the very end of this. However, Groovy and Kotlin has a really interesting feature, and that is if the lambda expression is if the lambda is the last argument to a function, right? Argument to a function, then it is treated special. You can relate this to other aspects in life. You probably are thinking at this point, you're thinking, what else in life that is last is special? Oh, I know one for sure. In families, the last child is special, isn't it? Admit it. I know it because I'm not one of them. I know what parents do. It's special for the last children, isn't it? Yeah, that's how Groovy gives special treatment to the last argument. So if it's a last argument, it can step out, and you can see right there, we can say, here comes the total, and I can simply say in this particular case, you know what, pardon me, this is Java, right? No, I was teasing you. Java doesn't do that, but this is Groovy and Kotlin that has that special treatment. Java treats all the children fairly, and I'm happy with that, right? No, just kidding. But the point really is, in the case of Groovy, I can go back to this code and say, here comes the inject function, but I want to turn this into a lambda sitting outside, as you can see, and I can convert this to a lambda on the outside rather than being inside. That does make for the code to be a lot more elegant and concise and easier. And I'm going to do the same thing here in the case of Kotlin. I'm going to come to the fold function, but I can say, hey, I want to take the fold, but I want to write that as an outside that particular lambda, and I can simply write that outside and say, here you go. I want you to simply have this lambda being passed to this function, and I want to simply use it, and you can do that as well. So that becomes a nice elegant syntax. And of course, you can only do this for the last lambda to step out and use it. And that's basically what you have available right here. So we talked about quite a bit here about what does it mean to be imperative, declarative, functional. We talked about the function composition, the nature of higher order functions, how we can pass them around, the basic functions we use in functional programming, the filter, the map, and the reduce, and of course you iterate and print out the values and so on. We want to talk about a few more details that is going to take us straight into some critical things we need to keep our eyes on. And I'll also make a comparison between the languages as to how they deal with it and how we may have to deal with it. But I want to pause for just a second and see if there are any questions or comments so far, anything that intrigues you at this point, anything that you want me to explore a little bit more in terms of what we talked about so far. So if Neha has any questions that we have seen from the audience, I would definitely.
Hi, Venkat.
Yes, please. Yes, go ahead.
Yes, I do have some questions actually, and it will be a nice way to tackle them right now. So Himanshu has a question. So you were showing the imperative style and the functional style in the Java code with the thread constructor. He asked, is the bytecode still the same when you're passing a runnable to a thread constructor?
Oh, beautiful, beautiful question. I love that question. So this is where, there's a saying, right? A lifting tide lifts all boat or something like that. Well, Java did a wonderful job, and I'll share with you a little story about it. And I say this is a story because I salute people like John Ross at Oracle for taking this effort. And I think this is not just a story of, Java. I would say, Himanshu, this is a story of good karma, actually. And the reason I say that is when Java 7 was being developed, some developers like John Rose and other people wanted to really spend the time thinking about how do we really improve languages like Groovy and dynamic type languages on the JVM that were really exploiting nice meta programming, but they didn't have a good performance because it turned out that fundamentally the Java virtual machine, the JIT compiler rather, is statically typed. So they devised a nice mechanism called invoke dynamic. And invoke dynamic was actually created to support these other languages on the JVM. Well, as time went on, as they started working on Java 8 and Lambda expressions, so the obvious answer was, are we going to take these Lambdas and turn them into anonymous inner objects and then pass them? And that wouldn't really give us the benefit because more anonymous inner objects we create, the more garbage we create, the more garbage we collect. It's not going to have a good performance. Secondly, your bytecode is going to blow out with all these anonymous classes being generated. So the net sum will be a huge negative. And they were scratching their head. And then they realized, wait a minute, if we go back and re-implement invoke dynamic, we can use invoke dynamic to implement the Lambda expressions and how they are passed around. So invoke dynamic was rewritten for a different use case in the case of Java in Java 8. What is shocking is if you look at more recent versions of Java, more and more things, even like string class, has been modified to make effective use of invoke dynamic. And I call this a story of good karma because they really wanted to help other languages and developers using other languages. And that initiative was not needed for Java at all. And after finishing it, that turned out to be one of the most important changes in Java because the number one user of that feature today is Java and almost every language on the JVM. So doing good things is actually really good. And it's a huge payback. That's a story of good karma, but really good question. So if you go to the bytecode and look at the bytecode, you will see invoke dynamic all over. And that's basically the story of how it's implemented.
Thank you. Thank you so much, Venkat. That was, I didn't know about that actually. So it was a new thing that I learned today. Kawakami is also having a question. He's asking, are reduce and flat maps similar?
Oh no. So good, very good question. So here's a way to think about it. Reduce is a terminal operation. It is what you're doing finally to fold things together. But I'll give you like a 10-second on what you can do. So suppose, let's say you have a 1-to-1 function. So you give an input, it gives you an output. Then use map to transform. On the other hand, you say, suppose you have a 1-to, let's say, many function. Then you use flat map to transform. So this is one of the easiest way to remember it. So in other words, so here's a way to think about it, right? Suppose I have a trivial example. Let's say I have a person and I have an age of a person. So given a collection of people, I can do a map and I can get back a collection of age. So that's a really nice operation. But if I have a person and now I get a collection of email, right? Because we all have multiple emails. Now what's going to happen? Given a collection of people, if you say, for example, map, what are you going to get? A collection of email, right? Well, that kind of smells a little bit. You don't want a collection of email. What do you really want? You say, but given a collection of people, and I'm going to put a little question mark here, I want a collection of email. In other words, I want to take the collection of email and flatten them out after mapping. So in other words, I want to map and flatten. Well, Neha, let me give you a little story again here. Here's a funny thing. If for people who are at home, if you especially have children around you, I invite you to try this. So call your children and ask them to say map flatten, because you're mapping it and you're flattening it, right? So ask them to say map flatten. Go ahead and you say it yourself. Try it. Map flatten. What do you notice? About the fourth time you say map flatten, you feel a sharp pain right here in the joint of your jaw. And the people who created this are genius. They realized if they call it for what it is, which is mapping and flattening, and you call it map flatten, we have a broken jaw at the very end of it. So they wanted to save humanity. So they called it flat map. Now try saying it, flat map. Notice how it rolls off the tongue, flat map. There's one movement of the jaw, not that awkward movement. So flat map is really map and flatten without breaking the jaw, right? So that's the story of flat map. You map it and you flatten it, but you call it in the reverse order as a flat map.
Oh, that was a good one. Himanshu has another question now, actually, and this is also one of my pain points, which I felt in the initial days of learning Lambdas. Why is it so difficult to do exception handling inside Lambdas?
Oh, very easy answer. The reason it's really beautiful, again, beautiful questions. I love this group. Beautiful questions. And this is one of the key things to really keep in mind. And once we realize this, it's like a light bulb goes in our head, right? So in other words, exception handling is fundamentally an imperative style, a style of programming idea. So essentially, here is an example, right? Imagine a friend calls you and says, hey, my good friend, I've got a flat tire. I'm in the middle of the freeway. What should I do? If you are a bad friend, what you will tell your friend is blow up the car and go back in reverse order. You wouldn't ever say that to a good friend, isn't it? What you will tell your good friend is, my friend, your safety is important. Very carefully, keep moving forward and pull out and get out to the sideline, get to the shoulder and exit the freeway safely. So in other words, in functional programming, right? In functional programming, we do not blow up, right? Instead, what do? We move forward downstream all the time. So when you have a problem, you don't blow up your pipeline. That's an imperative style idea. So what you need to do is, first of all, I'm going to say exception handling and functional programming, right? Functional programming are, I want to emphasize this, mutually exclusive. So this is the reason why it is so hard. It is hard because we are trying to do something that's fundamentally doesn't fit into that paradigm. So what do we do then? We have to treat error as a form of data and move it forward, first of all, and deal with it downstream. Now, if you look at Scala, if you look at Haskell, if you look at Reactive Stream API, they all, in one way or the other, give you a mechanism to do exactly that. They say, here's a problem, let's continue with the pipeline, let it keep pushing it forward, deal with it downstream. It's just the Java Stream API doesn't give us that, because the intentions of Java Stream API was different rather than giving a full-blown functional API. And that's the reason why we find it hard. But we need to realize we shouldn't be doing exception. We need to be designing differently in functional programming for that.
Nice. Thank you so much. I think I'm seeing the last point in, well, while doing some Scala code, why is it different than Java? So that gives the answer. I have one more question. Darshan is asking, can you please share some pointers on debugging functional code as well?
Oh, Darshan, I don't write bugs, so I don't have an answer for you. No, just kidding. Well, no, that's again a beautiful question. And Darshan, what I would say is, if I ask you, let's step back for a minute. If I ask you, hey, is it really hard to debug Java code? And you're going to say, oh no, Venkat, it's really easy to do. I say, oh my God, thank you so much, Darshan, because I'm creating 1,000 threads over here. And you're going to say, get out of here. Well, why is debugging hard for multi-threaded code? Not because it's not Java, right? It's hard because multi-threaded code is going to be non-deterministic. It's a paradigm shift. Well, that's exactly what we need to understand. And I love this question because it's a nice segue into where we are going. And that's a beautiful question because, Darshan kind of laid out the grounds for me and said, walk over, which is exactly what we're going to talk about. When it comes to functional programming, we need to keep in mind about the way functional programming works, the semantics. When you look at a piece of code, you need to know that the evaluation may be a lazy evaluation. Once you understand it's lazy, debugging becomes easier because you anticipate when it'll be called. Then you put your breakpoint and start debugging. Secondly, I would insist one thing very clearly. I insist never write multi-line Lambda expressions. So if somebody does the following, if they go in and put a curly brace and start writing multiple lines of code, that is a very, very, very bad practice. We shouldn't allow that because that makes debugging really hard because this completely lost the benefit, if you will. It lost the benefit of having that nice, concise syntax. But if you roll this into a separate function, you can put a breakpoint in the function and you can debug knowing when the function will be called lazily. And lastly, if you're using tools like IntelliJ IDEA, there are visualizers that show you how this computation is done. That can help you to conceptualize the concept really quickly, and that can ease the pain of debugging. And finally, I would say, if we write automated tests around the code, debugging becomes easier as well, because rather than testing the whole thing, we can take a unit and I usually put a breakpoint in the unit test and I start debugging, and I cannot tell you how many times, right? I put a breakpoint in the unit test, I start debugging, and within seconds, even before I go to the function, I'm like, oh darn it, I know what I'm doing, because it really gives me the opportunity to really focus on one narrow area. So good quality code, avoiding multi-line lambdas, understanding the semantics, and using the visualizers and debugging from the unit test. These things can make our lives a lot easier in general when it comes to debugging lambdas as well.
Well, thank you. Thank you so much. I have one last question. I think for now, it's from Krishnamurthy. Can we touch upon the performance factors like time versus space complexity of using filters, map, reduce, as we all use together?
Yeah. So one of the key things I would emphasize in this case is you want to keep in mind that the order of evaluation, right? What we talk as a big O is really the same when it comes to imperative and functional style of programming. In fact, I'm going to expand on that in the next few minutes. So I'll get to that, Krishnamurthy, in just a few minutes, because that's a really important question as well. So it's in the same time and space complexity for most part, if the language is doing it correctly. So there's a bit of a longer answer, but again, you also are laying a nice ground for what we're going to talk about. So let me talk about that. So that, thank you so much for those questions, and also Nihya for bringing that up in here. Let's talk about some of those to narrow that down in terms of pure functions and lambdas and where they fit in. So one of the things I want to emphasize here is we want to make sure that the lambdas are actually pure functions. That's our responsibility, to be sure that they are really pure functions. Let me give you an example just to illustrate the point. And I'm going to show that to you in the case of all these three languages and illustrate the point in here. So before we go into that, I want to emphasize one thing here is about pure functions don't have side effects. So that's the very first thing you want to keep in mind. The second thing is pure functions are idempotent. So you can call them any number of times and they will give you the same result every single time. They are idempotent functions. But I'm going to say, what are the rules of purity? And I'm going to say there are two rules of purity. Everyone will agree to rule number one. But many people don't think of rule number two. But rule number two is extremely important. I'm going to say rule one is necessary but not sufficient. So what's rule number one? A pure function does not change anything that is visible outside. And everybody can give a nod, right? We all agree. A pure function does not change anything that is visible outside. So if there's a change, you keep it to yourself. Don't show it outside. But the rule number two is equally important. And that is a pure function does not depend on anything outside that may possibly change. So this rule number two is something most of us don't think about, but it's an extremely important rule to think about. So let's put that on the back burner. We'll come back to it in a few minutes, but let's talk about lambdas really quickly. So let's say in here, numbers is equal to list of 1, 2, and 3. And I'm going to say numbers, let's say numbers dot stream, and I'm going to say a dot map. And given an element times 2, and I'm going to store this away into a variable called stream equal to. Then I'm going to say a stream dot for each and system dot out and print line, and I'm going to print it. So when I run the code, you can see the result is 2, 4, and 6, not a big deal. But when you look at this is a lambda. And why do I emphasize it's a lambda? So I want to emphasize what a lambda is. Lambda is an anonymous function with no dependency on anything external. So I want you to stare at this lambda very carefully. If I ask you, what is E? You say E is a parameter to that function. Hey, that's an input given to me. And what is 2? It's a constant. So this lambda is like a well-fed baby, right? It's happy. It doesn't have any problems. It's not feeling cold or hot. It's absolutely nice and resting. So that's basically what a lambda is. Has no dependencies to anything outside. That's a lambda. On the other hand, if I take this code right there, and if I say instead, if I were to take this out and say, hey, this is going to be a times a factor. Now you say, what in the world is this lambda doing? Well, what is E? Oh, E is the parameter to the function. Just look at only the highlighted part. E is the parameter. Great. Hey, what is factor? Oh my gosh, I don't know what a factor is. It's not present here. So what do I do? Well, I have to search around for factor. So what does the compiler do? The compiler has to look around to find factor. Well, there are two ways to search it. And one way is called lexical scoping. So lexical scoping is look for it in the defining scope of the lambda. So you go over and say, where is the lambda defined? Oh, the lambda is being defined in the main. So let me look in the main. If it is not in the main, or look in the defining scope, right? So you go to the defining scope, and you look for it. So I look for it in the main. If it's not in the main, I look in the static context of the class. So in other words, what does the compiler do? The compiler has to bind or close over to the scope, to the defining scope for a factor, right? So the compiler has to bind or close over to the defining scope for factor. Now this, now again, if you have kids around you, this is a nice exercise. Ask them to say, close over several times really quickly, over and over and over, close over, close over, close over, it begins to sound like closure. So now you know where closures come from. So this is a closure because it closes over the scope. So in other words, what's a closure? And I cannot emphasize this enough. A Lambda does not have any reference to external state. On the other hand, a closure carries a reference to, and I'm going to add this is my parenthetical, better be immutable external state. And some people have this notion in their mind that closures give them a free ticket for impurity. That's misguided, and we should never permit that thinking. So a closure carries reference to an external state, but it better be immutable. And this is one place where the languages differ from each other. So I'm going to give you a quick example of that right here to illustrate that problem. So if you go back to this code right here, and if you said in this particular case, a factor, and I say a factor is equal to 2, and when I run the code, you can see the output is 2, 4, and 6. However, if I were to look at this, the Java compiler says this better be, final. So if you notice, it's happy. If you don't put final, it is considered to be effectively final. So what does effectively final mean? It's as good as being final. That's what it means. So now if I say over here, factor is equal to 2, the compiler is going to give us an error, but guess where? The compiler gives us an error on line number 10 in this particular case. So line number 10, it says, local variable reference from the Lambda expression must be final or effectively final. And Java is telling us, please don't do this. Java says, if you do this, the result is going to be unpredictable. How so? If I go back here and say factor equal to 0, and if this were permitted, what is going to be the response of this code? Well, it's going to be confusing, error prone, and that is because this function is not evaluated until this function is not evaluated until the for each is actually called. That is lazy evaluation. Let me emphasize lazy evaluation really quickly, and that really nicely ties to the question that was asked earlier, and Krishnamurti was asking, how about performance? Let's talk about that really quickly. So if I go back to this code right here, we'll come to that in a minute. So that was an error in the case of Java, as you saw. Unfortunately, I'm using the word unfortunate. Unfortunately, if I say, for example, in Groovy, define numbers, let's say, is equal to, and I'm going to take the numbers 1, 2, and 3 like so, and I say define factor equal to 2, and I'm going to then say numbers, let's say, dot collect. And I'm going to say, in this case, given a element, I want to say element times factor, and I want to get the result out of it. So we'll say defined result is equal to, and then I'm going to print out the result like so. And if I run the code in this case, the factor is 2, but I come in here and say factor equal to 2, and notice Groovy does not stop us like Java did. Why? Because in Groovy, closures are permitted to have immutable variables. But in all fairness, that's true in Java also. If I were to move this to the class, right? So unfortunate, right? Sad, but what's happening here? If I were to say a factor is equal to 0 like so, the compiler doesn't stop us in this case. So in all fairness, Java is protecting us to some extent, but not beyond it. So the purity of a Lambda, or a closure rather, is our problem. We as programmers have to take that into account. And same with Kotlin as well. If I were to write the code in Kotlin, you're going to see that it permits me to change that. But having said that, let's talk a little bit about why this is critical to think about. Let's go back to this code and say, I want to take this element from here, but I'm going to call a transform function and pass that element e to it. Let's go ahead and write the public, let's say, static integer transform that takes a number as an argument right there. And I'm going to say return number times 2, but I'm going to say output. Let's go ahead and say a transform called for, and in this case, a number. So notice very carefully though, when I run the code, it says transform call for 2, 1, 2, and 3. But then if I go back here and say output, I am here, let's go ahead and put that line here and run the code. Notice where I am here is. So what we notice is this is run after, I am here, right? In other words, it's run when for each is called. That's why it's a terminal operation. But more important, here is the beauty of the functional pipeline. If you go back to this code, and if you said, let's say a 4, a 5, a 6, 7, 8, 9, and 10, that many values, but I'm going to say right here, stream dot find first dot or else give me a 0, and I want to store this into a result like so. I say result is equal to, right? And then finally, I want to output the result right here. So I'm going to say right about here, output, let's simply say done for now, right? I don't even care about that result. So if I run this code right now, what is going to be the output is the question. Notice it says I am here. It says transform call for 1, and it says done. It never called it for 2, 3, 4, 5, and so on. Just again to illustrate, if I said over here, something along the lines of dot, let's say a skip, and I'm going to say skip 2 and then find first. And you can see in this particular case, transform call for 1, 2, and 3 because I skipped 2, but it never called it for 4. That's lazy evaluation. So what does lazy evaluation mean? So lazy evaluation means a better performance. Why? Because operations are not done unless necessary, right? If it is not necessary, it doesn't execute. So so as a result, if you think about it, the imperative style, if you have written imperative style, what would you do? Do a break statement from your code. Same idea here. So the computational complexity is the same, and everything else is a wash in general. But in this case, lazy evaluation. So I want to emphasize this really here from the purity and the lazy evaluation. We want to really think about it very, very carefully. So here's what I'm going to say. If you think about this a little bit further, if I come to you and say, what's a big deal about object-oriented programming? And I'm going to say to me, one of the most important things is polymorphism, right? So polymorphism is probably the most important aspect of object-oriented programming. So I'm going to say polymorphism is to object-oriented programming as lazy evaluation is to functional programming. You take away polymorphism. I don't have object-oriented programming. I have object-based programming. You take away lazy evaluation. I don't have much of this. This is where we got to be careful about it. So first one to keep in mind, Java streams are always lazy, right? They're always lazy. If you go to Groovy, in the case of Groovy, the pipeline in Groovy are always eager. Of course, you may use Java streams in Groovy, and then we have lazy evaluation. So in this particular example, if you talk about performance, if you use a native pipeline in Groovy, to go back to your question, Krishnamurthy, you're going to have trouble with that because your performance is going to be rather poor because you do a lot of extra work. Not in the case of Java streams. Now, we know what's going on here. Java, always lazy. Groovy, always eager unless you use Java. What about Kotlin? Well, we know Kotlin is special, right? So in Kotlin, I write a transform function, and the transform function says, I'm going to take an integer value coming in, and I'm going to return an integer. But in this case, I'm going to say return n times 2, but I will go ahead and print out, let's say in this case, transform called for, and let's put the value that it's called for. But then I'm going to say a val, let's say numbers is equal to list of 1, 2, and 3. But I'm going to say numbers dot, and I'm going to say filter, and given an element, well, actually, it's just directly go to the map, right? So map, I'm going to say given an element, will transform the element given to us, and I'm going to store that into a variable here. Let's say result is equal to. But then I'm going to say result dot for each, and I'm going to then print out that particular value, a print line, let's say. So if I print it out, and I'm going to say in the case of Kotlin, like so, I'm going to say I am here right there and run it. So when I run the code, what do you notice in the case of Kotlin? Notice all that transformation was done, and you have an I am here. So what do we know from that? Hey, that's eager. But Kotlin says you choose. So in the case of Kotlin, you can say as sequence, like so, and then you can run the map after that if you want to. And if you do, notice I am here is in the beginning. So to summarize this is what we know so far, right? Java stream, always lazy, right? Always lazy. A Groovy pipeline, you can say, always, so always eager. And on the other hand, well, with a little caveat, right? Always eager, and of course, with a slight caveat here, except when we use Java Stream in Groovy. But in the case of Kotlin, you have eager or lazy. You choose, right? So you basically can choose whichever you want to, and the language gives you that flexibility. But having said that, I cannot emphasize this enough, that polymorphism is to object programming as lazy evaluation to functional programming. So functional programming is functional composition plus lazy evaluation. One last thing, functional programming emphasizes purity of functions, or programming with immutability, not because it is fashionable. So then why? Well, FP relies on lazy evaluation for performance, and lazy evaluation relies on purity for correctness. So that is the reason why we need to be extremely careful when we use the languages like Java and Groovy and Kotlin. They're all hybrid functional programming languages. They don't protect us. We have to protect ourselves. So if we don't guarantee purity, you lose out on correctness, because lazy is not going to turn off in Java. It's going to assume you are made the functions pure, and you get incorrect results. And as a result, what good is performance when your code isn't producing the right results? So functional programming, essentially, that is something to keep in mind, is functional programming relies on lazy evaluation for performance, and lazy evaluation relies on purity for correctness. So as much as these languages are all similar and different in their own ways, we can benefit from their conciseness. We can benefit from their power. We can benefit from their syntax, but we should never lose sight of their semantics. And the semantics of functional programming relies on purity because performance relies on laziness, which counts on purity. So be careful using these languages. Never lose sight of the semantics while you enjoy the syntax. I really hope this was useful. Thank you so much for having me.
Thank you so much, Venkat. So now I have a question. So the way you taught about pure functions, is it safe to say that having immutable objects being used as a function arguments are safer to use because they will always give you same results and it is easy to predict them?
They are, except here is one of the challenges with what we do. For things to be correct, everything has to be done correctly. For things to be wrong, we just have to mess up in one place, right? That's unfortunately the world we live in when it comes to it's not a single point of failure, it's a failure every corner you turn if you're not careful. So I completely agree with what you're saying, but that is not a guarantee because we got to look around for every single place. For example, you might receive an input argument which is final, but because you have lexical scoping, you are able to reach around to variables which are in the defining context. And if those are not pure, you are not mutating them, but you're depending on them and they are changing. That can affect the result of your code as well. That's the problem, is you have to kind of keep your eyes 360 degrees and look for problems everywhere. Good code reviews, good discipline, and generally speaking, right? Once we are lapse on good practices, we lose the sense to identify these. That's why when I write code, I always scream, "Oh my gosh, you shouldn't do this!" And the reason is we don't want to let those senses dim down, because if they do, the errors creep in and it increases the cost of maintaining later on. And it's no more fun programming in functional style because the language was not protecting us for whatever good reasons they can't, but we have not protected ourselves either. So we got to look a lot beyond that as well.
Very good point. Thank you so much. And actually, this makes another observation I recently thought about. So I was so close to imperative style programming, and when I started learning functional style, it looked like writing a unit test became more and more easier.
Oh, wow. Yes, absolutely. That's music to hear. Keep going.
That was like, I remember when I initially started writing those imperial style programming, and it was hard to think about the possible outcomes. And since with functions, the possible outcomes, it gets so much easier and quicker to write the unit test and get over with it.
So yeah, you're absolutely correct. The purity makes it easier because guess what? When something is idempotent, idempotency makes testing easier, right? That's one of the biggest benefits you get out of this because it doesn't have any side effects. But not only that, now imagine you want to stub and mark your code. You can easily create a stub for a Lambda by just creating another Lambda, which returns a fake or a canned response. So not only testing is easier, replacing your dependencies with a stub or a mark is easier as well if your dependencies are a functional interface.
That's true. I have one question from Suhas. What are the major functional features that are available in languages like Haskell that are not available in Java?
Oh yeah, that's a beautiful question, Shuhas. Thanks for asking that question. And Haskell is, as we know, is a purely functional programming language. So I jokingly often say, if you write code in Java and versus you write code in Haskell, well, Haskell is going to look at you and say, "I'm watching you, right? I'm not going to let you make any mutability." And I say often, Haskell doesn't just allow you to write code. It follows you home, sits by your dinner table and stares at you and says, "I know what you're thinking. Don't have those thoughts of mutability," right? So it's a language which is extremely strict in enforcing it. When you program in Haskell, you have to go through quite a bit of constraint to work with that restriction of mutability quite a bit. Haskell is fundamentally a language which is lazy. So in terms of programming, there are two concepts. One is called applicative order, and the other is called a normal order. Applicative order is a function is called when you apply it, when you call it. A normal order is it doesn't get called until that function is actually invoked later on. So here's a little example to think about it. Suppose you write a function, let's say in the case of Java, you say foo and you call bar. Well, in this case, bar is called before foo in Java. This is called applicative order, right? Which is what we are all mostly used to. In Haskell, on the other hand, foo is called before bar. And bar is called within foo, where the data is needed. So this is called, in computer science, this is a funny word, by the way. They call it normal order, but I would rather say this is abnormal order, right? Because nobody uses this other than few of those languages, but if we come up with weird terms, that's a normal order. So that's one fundamental difference, is that in Haskell, you have a normal order compared to an applicative order. But take that beyond. In the case of Haskell, you have tail call optimization already baked in. In Haskell, you have the ability to have memoization done automatically. So when you call functions, it'll store the results as a thunk. And the reason it stores as a thunk is in Haskell, functions are immutable. So Haskell says, oh, you called me. If you ever call me again with the same input, boom, I'll give you the result right away because it's immutable. So there's a lot of things that Haskell does. And finally, I will add one more thing, not related to functional programming. You should never say Java or C++ or C# or any of the languages is statically typed like Haskell. That's not a fair statement at all, because once you look at the static typing of Java and compare it to static typing of language like Haskell, you will notice it's a completely different scale that we are dealing with. The type system in Haskell is enormously more powerful than most of us have experienced in a lot of what we claim as statically typed language. That's another difference, just to mention a few things.
Nice. Thank you so much. A few more comments or questions. Can you comment upon the Arrow FP library for Kotlin? Is it worth using, or when to use it?
I would say definitely yes. But one thing I always say about any library, it doesn't matter what library it is, you always want to evaluate the cost of using it versus cost of not using it. So if it is something where, so in other words, what I want to emphasize is never use a library for the sake of using it or because of infatuation. You want to evaluate it and say, here are the ways in which we will clearly benefit in our code, and here is the reason. You need to have a really good reason, right? And I cannot give you that reason because I don't have the context of your application. I never tell anyone you should use a library. I always say, let's evaluate the context. Let's understand what you're doing with it. Let's understand the cost of using it. Let's understand the cost of removing it if we have to remove it in the future. Everything becomes obsolete over time. The language evolves. There's going to be incompatibility with things. So I would normally like to have a smaller surface area on my dependencies. So I would use the same concerns for every single library I use. But having said that, it's definitely a respectable library. A lot of people have used it. It is exciting, but don't use it without evaluating for your own reasons.
Thank you. Thank you. One last question is, learning category theory, will it help with the functional programming?
Well, let me say, we always should be learning. But are you going to be a better programmer because you know something? I don't think so. And I'm not suggesting for that reason you shouldn't know it. To become a better functional programmer or anything, even a programmer in general, I would say, one of the things I'm going to go on a tangent here to answer that question, if you don't mind. And, I'll use the words of Newton. Newton said, I see farther away because I'm standing on the shoulder of giants, he said. Well, this was Newton, by the way, saying that he benefited by learning from others and the work others have done. And if Newton can say it, I definitely have to be humble enough to accept it, and I do. And to me, I can tell you a clear difference in my life when I used to write code when nobody looked at my code, and the time when others started critiquing it. And when others reviewed my code, others told me what I could change, others showed me how I could improve. That to me made me a better programmer than I was. I'm not saying I'm a good programmer or a bad one, but I'm definitely better than what I was. And to me, if you want to become a better programmer, functional or otherwise, I would say you do that by writing code, by getting critiqued, by refactoring it, and going back and writing it. So will category theory help you? Yes, it will. Will monads help you? Yes, it will. Will any other concept help you? Yes, it will. But it will not help you in isolation. It'll help you in applying those concepts by way of writing and rewriting and rewriting. So be willing to write, be willing to make it look really bad, and then come back and improve it and compare and contrast it, and then have other people critique you. And then I think we can have a chance of getting better. So in combination with that, I think everything else will make us better.
Well said. Thank you so much. I think we have a lot of questions coming in at the last minute, but I'll go with this one because this looks interesting. What are the rules we need to follow when converting Lambda to method reference? This is Satish's question.
Yep, good question, Satish. Actually, it turns out to be really simple. And I'm going to say a word I like to use is called a pass-through lambda. So what is a pass-through lambda? A pass-through lambda is really a lambda that does not do much at all with the parameters that it's given. So for example, I'll give you two examples of a pass-through lambda. Given an element times 2 is not a pass-through, right? Because you're taking the element and you're doing something with it, right? So that's not a pass-through. On the other hand, if I take an element and I say output the element, right, I would say this is a pass-through lambda. Why? Because I didn't do anything with E, I just passed it through. Or another example is, given an element, I'm going to say E dot some function I'm going to call on it. I'm going to say this is a pass-through lambda as well in effect. So pass-through lambdas are pass-through lambdas really take the given data and they simply, my keyboard is misbehaving here. So given an element, you can say e.func and you're calling it, I would say that is an example of a pass-through lambda as well. So in other words, a pass-through lambda simply passes it through, either calls a function on it, a method on it, using it as a receiver, or pass it as a parameter. In other words, you're not taking that value and performing computations with it. So the easiest way to think about a method reference is to identify whether it's a pass-through lambda or not. Well, another way is look at the light bulb in your IDE and you click on it, it swallows a lambda and puts a method reference. That's another way to do it. Here's one more thing I would emphasize. If you ever find a colleague who has written a multi-line function like this, right? I'm sure you all have seen this, right? So if you see a person who has written this code, right, please don't get upset at them. They're not bad humans, they're just bad programmers, and they can get better. So you immediately take this and say, hey, I'm going to call the E and roll into a function, and then you pass that E to it, and then you move that body into a separate function. And the minute you do, you realize that ugly, unwieldy, big lambda became a beautiful, single, nice lambda. And I want to really emphasize this, if you don't mind, because I see a lot of people making this mistake. I'm going to say lambda or glue code. If you can Google for that, you will find that reference, lambda or glue code, right? That's basically what you want to Google for, lambdas or glue code. And I want to really emphasize, never write multi-line lambdas. But the beauty of this is the following. The minute you roll it into a function, that unwieldy lambda goes away, and guess what? Now you can take that Lambda and you can roll that into a function very easily with almost no effort because it became a pass-through Lambda. So you went from this unwieldy, scary Lambda to a glue code Lambda into a method reference very quickly. That's another benefit you will get to identify them. Sometimes you don't see them through your eyes directly, but a little refactoring reveals them pretty quickly.
Nice. I want to see one more thing actually. I just noticed that you with method references, you don't have to deal with the name of your lambda just before you have lambda expression, right? So you don't have to worry about that. What is your context right here? So you can just get rid of it.
Beautiful observation. So I love that thought. If you give bad names, the bad names disappear with method references. What a lovely thought, isn't it? Absolutely. So if you're struggling with the name, think to see if you can remove it entirely by using a lambda expression. I love that thought.
Well, this was from one of your previous talks, so I remembered it. Thank
Well,
you.
absolutely right. We can apply that very easily and benefit. So definitely, it's one way to really make the code better.
Thank you so much. I think we have covered almost all the questions, and thanks a lot for answering them all very patiently, and really enjoyed asking you questions. So that was my dream as well. I'll pass it off to Frank and Barry.
Sounds good. Venkat, thank you very much. That was thank you for sharing that information and insight into functional programming. It's amazing that something that was invented about 70 years ago is now becoming quite popular. Seems like a lot of things come from Lisp, right?
It is absolutely.
So again, thank you very much. And thank you very much for the Agile Learner. So we're going to raffle off a pass for Agile Learner, agilelearner.com. So Venkat is the founder of agilelearner.com. There's just tremendous amount of information there. So please visit that site and check out some of the content there. It's really amazing stuff. So thank you, Venkat.
I do want to say thanks to all the questions. I really enjoyed it. I wanted to really say I really appreciate that. And thanks for Neha to be so patient to read them out and also to ask such brilliant questions. So thank you so much. I really appreciate that. Thanks, Frank, and thanks everyone else as well.
Sure, and I know that it's your dinner time now, Venkat. So we'll let you get going. Again, thanks a lot. We'll do the raffle now, so if people want to hang out for the raffle. But Venkat, I know it's your dinner time, so we'll let you go.
Thank you. Appreciate it.
Thank you very much.
Thank you.
So Barry, you can handle the four things we're raffling off, right? We're raffling off the IntelliJ licenses and the Agile Learner pass.
We are indeed. We are indeed. Can everybody see the raffle wheel? Yes, yes, yes. The raffle wheel is visible. I don't hear that it is.
Hold on. I think now it should be visible.
Yes, I see it now.
Excellent. Okay, here's what we do. If you're interested in winning one of our prizes, type a number between 0 and 29 in the chat, and I'm going to spin the wheel. The people who are closest to the number that we spin, modulo 30, are the winners of our prizes. In case of a tie, we're going to have a pie eating contest at Katz's Deli a month from now. And it looks like we've got lots of numbers. Oof, we're really going tonight.
It will be hard to search the person.
Yeah, I'm going to leave that to you, Neha.
I'll keep my eyes open.
Okay. The cheesecake eating contest, I'm afraid not. A roast beef eating contest. All right. Yeah, no dupes. Frank, what's your opinion? Are we ready to roll?
I say we give it a spin.
Okay, MG, I think you're the last participant here. Entries are closed. Here we go. And I said, here we go. There it is. Let's see if we can get some music with this. Not sure. "27." Who's closest to 27? Neha, are you scanning this?
We have Ganesh, who has number 27. Darshan Shah has 27. Ganesh Babu and Darshan Shah. 2 people.
And I see some 26s.
Yeah. Hold on. Were there a 26? Oh, Suhas has 26. Yes.
I think I saw 2 26s there. Yes, there are 2 26s.
We have 2 26s. We have 2 27 as well. Looking.
I see 2 26s and 2 27s.
Okay, those are our 4 preliminary winners. What I'm going to do is ask our 2 27s to each type in a number, and we'll roll again. The closest person is the winner of the Agile Learner. Oh, do we have a duplicate here?
Ganesh Babu has 9 and 27. Both, yeah.
I'm afraid that disqualifies you.
Yes, that disqualifies you. Definitely.
So I think we have 3 winners. Let's stick with that. Number 27 gets first choice, and please, all 3 of you winners, send your contact information to info@javasig.com. info@javasig.com. And thank you.
Great. Okay. Congratulations to the winners. And of course, we want to thank Venkat, who's not here anymore, but thank you, Venkat. And we'll see everybody at our next meeting. So we do have a hands-on workshop coming up on April 27th on JReleaser, where that's Andres Almaray. That should be quite exciting. For those that don't know, we do have our hands-on workshops regularly, in addition to our monthly meetings. And stay tuned for our monthly meetings. Just stay tuned to Twitter. We have our Facebook, our website, javasig.com. You know where to find us. So stay tuned for our next meeting. So thank you all, and we'll see you soon.